लाइव शुरू कर दीजिए साहब, हो गया टाइम।
Hello everyone, welcome to one more session of live discussion with Ashwini Kumar Sinha and Suresh Dwivedi. Today our topic of discussion is AI accelerators versus AI processors. So my first question is, what is the difference between AI accelerator and AI processor?
Actually, an AI escalator and an AI processor both serve to enhance the performance of the artificial intelligence task, but they differ in purpose, architecture, and the application. For example, in case of the purpose, when we are considering about the AI accelerator, so it is the specialized hardware designed to speed up the specific AI workloads, uh, like deep learning, interference, or training, while working alongside a primary processor, CPU or GPU. It's not a standalone processing unit, but a complement of the main processor for the AI related task. When we are talking about the AI processor, actually it is a more generalized standalone processor designed to handle a broader range of the AI task efficiently. It integrates AI capabilities directly into its architecture, making it suitable for device where AI is a core function. When we are talking about the architecture, in case of the AI accelerator, it is focused on optimizing a particular type of the computation, such as the matrix multiplication for the new neural network. Example includes tensor processing unit, TPUs, normally known as neutral processing unit, NPUs. When we are talking about the architecture of AI processor, it combines AI specific functionalities with the general purpose processing with features. It often includes uh, integrated AI engines, making it versatile for a mix of AI and the standard tasks. When we are talking about the application, in case of accelerator, typically it is used in high performance computing environment or embedded system to enhance a specific AI application. For example, data centers, TPUs for the Google AI workloads, smartphones, and NPUs for the real-time images processing or voice recognition. When we are talking about the application of AI processor, it is used in the system where AI is deeply integrated, such as autonomous vehicle, robotics, or the AI first devices. These processors power both AI computation and standard computation needs. When we are taking, for example, when we are AI accelerators, for example, NVID, NVIDIA, CUDA cores in GPUs, Google's TPUs, Apple's neural engines in part, and example of the AI processors are Intel's Movideus chips, Qualcomm's Snow with integrated AI engines are custom chips in device like Tesla, FSD, full self-driving computer, etc. So in brief, AI accelerators specializes in speeding up specific AI tasks as co-processors, while AI processors are general purpose chips with integrated AI capabilities designed for the standalone operations. That's all.
Okay, so you talked about AI workload. So how do AI accelerators improve the performance of AI workload compared to the traditional CPUs?
Okay, so as compared to the traditional CPUs, if you execute any kind of AI processing or training the machine learning models, they run on the CPU in multiple threads according to their capability. So as either they are single core, dual core, or 8 core. So all these processing need to be done in the in a thread in same 8 core or 4 core or 2 core CPU or chip that is there for the processing. So isn't that much of fast, and it didn't give you that much of acceleration to the process, because it has to be doing the thread, and it has to it has to be process the instructions one by one. And if you go for the machine learning, if you go for the machine learning training the machine learning model or doing the AI processing, then that requires the parallel processing and that requires the complex matrix calculations, 3D 2D vectors of the machine learning models. So they suffers in these things. So if we use the AI accelerator, how these AI accelerator is different from these, let me first tell you the difference between these. So AI accelerators are actually the extra processor that you add, extra unit of processing that you add to the main GPU, and it works hand in hand in parallel. This is called AI processor. The AI accelerator use the parallel processing. So it's kind of parallel processing. So one processing is done by the internal CPU, GPU, NPU, whatever there in your laptop or whatever there in your system, and then these accelerator, what do these accelerator do? They join hand in hand with them and do the parallel processing. So one processing done in these NPU, GPU, whatever you have in your system, plus these external chips that you add as an accelerator is joining the hand with them and doing the processing in parallel with them, and this helps you in increasing the processing power and also the time, because of the parallel processing. Because they are not working in the threads, they are not working in the one by one instruction set. They are both the one, two or multiple instructions are been executed at in the parallel. They are both working in parallel, they are both working at the same time. So this is why we call AI accelerator. What is the accelerator? What do the accelerator do? What the word that accelerator mean? It accelerates the task. It accelerates. It speed up the task. So if you are using any kind of NPU, GPU, TPU, whatever you have in your or CPU, whatever you have in your system, laptops for the AI processing or machine learning model training. When you add accelerator, you accelerate that task of training. It's accelerator, speed up the time, and it's to help them in in accelerating and speeding up the task by the parallel processing, and it helps them in various ways, like doing it can handle the multiple of task at the same time, accelerating the time. And it helps them in the models or AI processing, where there is a multi-dimensional matrix, so making the complex calculation for them. And it's also increased the bandwidth of the whole workload, and it can handle the whole task in much efficient way, and without stressing out the main NPU and GPU in your system. So I hope I have give you the answer.
Okay. Okay, so can you explain the role of AI accelerators in machine learning tasks like training and inferences?
Yeah, so if you are using, suppose that if there is certain kind of machine learning tasks that you have. So now you have one it need to be that in machine learning, what do we do? We put some kind of data set that need to be learned, that need to be trained using those data set. So if we're training using the normal processors that already we have in our system, then using those internal whole what's say internal capability, it's run the task and try to train the model in threads, or in one by one. I have already told you. But when you add an accelerator, it's do the things in parallel along with that. So if it's the multi-dimensional matrix, it's a multi-dimensional calculations, 2D matrix or 3D matrix, like you might have know those who are working in the ML model. There are 2D matrix, 3D matrix that form the numerical value, and it do the calculations and make the ML model, train the ML model, form the neural network inside. So all those things happen when it's all those things happen only in the inbuilt capability of the system. Then it takes time, and it's lots of stress and thermal stress, and processing stress on the internal capability of the system. But when you add the AI accelerator, it's join the hand and do those tasks, share those tasks between those internal capability as well as external accelerator chip, and they join hand together, and they share the tasks in between them for those calculation, and this speed up the whole things. And this is how they help each other, and they accelerate the whole process in training the ML model and doing the multi-directional 3D matrix, 2D matrix calculation. So this is how the AI accelerator helps you in training the especially when it's the multi-directional 3D matrix calculations and something like that. It's especially help in those kind of calculation when you add the AI accelerator.
Okay, so what are some popular AI accelerators in the market today, and how do they compare with each other?
So there are I will invite the Suresh sir as well to answer this. So there are few accelerators I have already worked. Let me share my experience, and let me share the few more thoughts on this thing. So one of the AI accelerator that is readily available in the market is by the Intel. That is, you can call it the Intel Neural Computer Stick 2. It's the blue color, very small USB size stick. You can search if you are watching here, and you can search in the phone or laptop, wherever you are watching. It's a very small stick, side USB stick kind of system, and you can simply plug it into your laptop. It's a very small size, and this accelerator will work along with you, help you in these kind of tasks. So one is the Intel Neural Stick Computer Stick 2, and there is another AI accelerator that is from the Haloid chip, that uses the Haloid chip. So it is for the Raspberry Pi or NVIDIA Jetson, or some other SBC PCs, SBC systems out there in the market. Like you might have used the Raspberry Pi. Most of the people who are working in the low level of computer vision or machine learning training, they might have using the Raspberry Pi or NVIDIA Jetson versions for the training and working with the AI models. So for those kind of things, those kind of SBC, there is a hat available from the Haloid that is that gives you 26 tops of processing power in at that size only. This you can search it right now if you are using the web. So that is from the Haloid. Say, well, then another is from the interneural sticks, and there are few more AI accelerators are also coming, and there are few companies like BrainChip, Akida. Those are working for making these kind of AI accelerator. So I also invite the Suresh sir to give his thought on these kind of new AI accelerator that is known by them, and that they have that is used in life.
Hello. Apart from that, there are various types of the popular AI accelerators, such as the NVIDIA tenders core part GPUs, and another is the Google Tensor Processing Unit TPUs. Another is the Apple Neutral Engine ANE, and there are several. One more is the AMD ROC with the MI series GPUs, and next one is the Intel Havana, Gaudi, and the Goya, and another is the Qualcomm Hexagon DSPs. So there are various types of the accelerator. Each accelerator has its niche depending on the workload, performance, requirement, and budgets. The choice often depends on the whether you prioritize edge computing, cloud-based scalability, or all-purpose versatility.
Okay, so how does the architecture of an AI processor differ from the conventional CPU or GPU?
Actually, the architecture of an AI processor, which is also known as the AI accelerator, is specifically optimized for the types of the computation and the data handling requirement in artificial intelligence and the machine learning workloads, making it distinct from the conventional GPU, central processing unit, and the GPU, graphic processing unit. Actually, it depends on the purpose-built design. In case of AI processors, it is designed specifically for the matrix multiplication, vector operations, and other linear algebra tasks that dominate AI workloads. They include specifically hardware like tensor core or systolic arrays to accelerate these operations. When we are talking about the CPU, CPU central processing unit, so it is basically it process optimized for the versatility and the wide range of the task, often emphasizing single thread performance and the low latency task switching. When we are considering about the graphic processing unit, it optimized for the parallel processing, originally designed for the rendering graphics. Their thousands of the cores are well suited for the some AI tasks, but are not purpose built for them. When parallelism, in case of AI processor, highly parallel architecture with the thousands or million of the small efficient cores working simultaneously, often organized to process large data batches, etc., in neural network. Typically, the GPUs, CPUs typically have limited number of powerful cores, for example, 4 to 64, designed for the sequential and the multiplexing workloads. While in case of graphical processing unit, it offers massive parallelism with the hundred or to thousands of the cores they have. They are less optimized for the AI task. And another parameter is the architecture, data flow optimization. AI processors, it uses the optimized memory hierarchies and the on-chip memory to minimize data movement, which is a major uh, bottleneck in AI tasks. Many implements near data processing to reduce the latency. Another parameter is the process precision and the numerical formwork. AI processor supports lower precision formats like in 8BF16 or FP16 to improve throughout and the powerful efficiency, as many AI applications don't require full 32-bit precision. And another is the power efficiency. AI processors are designed for the energy efficient in performing repeated AI specific operations, which are the critical for the data centers and the edge design devices. Another parameter is the scalability and the customized. Normally, AI processor often tailored for the specific AI framework or the workloads, such as training, deep neural network, or running interference at scale with the custom architecture like Google, TPU, NVIDIA's tensor cores, or the Apple neural engines. So in brief, we may say that AI processors are designed to maximize throughout efficiency and performance for the AI task, while CPUs and the GPUs are serve broad proper purpose, with the GPUs acting as a middle ground in their ability to handle workload more efficiently than the CPUs.
Okay, so what are the key advantages of using AI accelerator for AI workloads, and what challenges do they pose?
So there are lots of key advantages of using the AI accelerator for the AI workloads and the machine learning things or edge computings. So one of it is its high performance, and it is especially optimized for building and it is especially optimized, and its hardware is designed in such a way that it enables the overall performance of the whole system and allow you to do the calculations in multi and matrix calculation, 2D or 3D matrix calculations, and do the computational task in parallelly, and it is especially optimized for those tasks. So it helps the like if you are using the CPU or GPU that in your laptop, so it's not especially optimized for the AI tasks. They are optimized for the overall things like the graphics things or the or running other tasks as well. So they are not especially optimized for those things. But AI accelerator are built and designed to do these kind of specialized tasks only. So this helps them to increase the overall performance. And then second is the energy efficiency. The if you use the AI accelerator along with these kind of CPUs, traditional CPUs that we are already using, then it's optimized the overall computational energy to power ratio. It's overall computational energy to computation ratio. It make it more efficient, and power to power to computation ratio, like the amount of power that a single or multiple CPUs or GPU needed to use to do a particular task. The same can be said with the AI accelerator, and that can be done in more energy efficient way, and that is more and more in very much less time. And second thing, it provides you the data. I have already told you that it's provide the parallelism. Like parallelism means the parallel tasking, there are multiple of threads. Multiple threads are running in the CPU or GPU for a particular task, and then you add the AI accelerator to this. Then those multiple threads that are already running in the CPU or GPU task will shared with the external chip, the accelerator, and both all of them run in parallel. So multiple threads are running here in one GPU and CPU, and multiple threads are running here. So the overall task, that is, suppose that I have 100 instructions and 100 tasks and calculations that I need to do. So I have 4 core GPU. So all those tasks are divided in those 4 core GPU and done in the threads parallelly in those 4 cores. Now it takes the 10 minutes for doing those calculations in the thread for this one GPU or CPU that I am currently using. So if I add the AI accelerator, not this share the same task that is it's already done. That is that is what's 100 tasks. That 100 tasks which is shared between this and this, both of them, and it became 50 and 50. So this the overall time it is taking 10 minutes to do the 100 tasks. That now this task is divided into 50 threads run by this and 50 threads run by this. So total 100 of tasks will be done parallelly in at the same time. So instead of taking the 10-minute time for that processing, it now takes only 5-minute time of processing. And it also helps you in optimizing the energy. Like the whole task is taking the 10 minutes. So for the whole 10 minutes, it's this CPU will run in full performance, and it's consume the whole energy for the 10 minutes. Now it's we have a AI accelerator that is more optimized to get take little bit of take less energy and gives you better performance. Now the whole task that is need to be done for the 10 minutes, now it is taking only 5 minutes. So all the other 5 minutes that you save, the whole power saving is there for the 5 minutes also the performance can be done in, and it become faster. So one is the high performance and a specialized design for the AI acceleration. Second is the parallelism, and then third is the energy to computation ratio that it provide. And second, and then another advantage that have already Suresh have already told you that is the scalability. We can scale up these AI model and training of these AI task with the help of AI accelerator in exponential manner. And second is the AI framework, supported AI framework. So these AI accelerator can be designed in a special way, and so that it can help you in optimizing optimized computing, optimized work for particular frameworks, for particular range of frameworks. There are many AI accelerators from the Intel or the Helloe that I've already told you about, or Nvidia, that are specialized and designed to take designed to AI frameworks like the TensorFlow, PyTorch, or CUDA, or CUDNN, all the different frameworks. Those who are already working in the machine learning things, or the AI task, then they might have familiar with these kind of frameworks like TensorFlow. That is TensorFlow, one from the Google, and then the PyTorch, then another one is CUDA, and there are many others out there. So these AI accelerators are specially optimized and designed for these kind of frameworks. So it gives you the ease of access and ease of performance, and it also gives you the scalability, the parallelism, it's reduced the latency. So suppose that it's also reduced the latency. Like I've already told you that if you are using one single CPU or GPU, whatever their capability of your system, and if you add AI accelerator, then both the tasks are done in parallel, and it's there the overall computation uh, uh, thing with each other, and the task get divided and learn parallelly. So it's reduced the latency between the threads to be run and executed, and it can run parallelly. If one gets slower, then it gives share the workload to the AI accelerator. If the AI accelerator get more workload, then it gets shared to the another one. So they overall they work with each other to optimize the overall performance and reduce the latency in the data set training, or ML model training, or AI AI computational, or running the ML model at the edge.
Okay, so how do FPGAs compare to GPUs and TPUs in terms of flexibility and performance for AI applications? Should I repeat the question? How do FPGAs compare to GPUs and TPUs in terms of flexibility and performance for AI applications?
Yeah, I think
So,
you are mute, sir.
Actually, the FPGAs, which is normally known as the field programmable gate arrays, and GPUs, which is normally known as graphic processing unit, and TPUs, normally known as tension processing units, each other distinct advantages and trade-off for AI applications, especially in the term of flexibility and the program. When we are talking about the flexibility, so in case of FPGAs, highly flexible, they as they allow for the custom hardware configuration. User can design a specialized circuit tailored to specific AI tasks, offering fine-grained control over the performance and the energy consumption. This flexibility is the ideal for the application that require custom data processing pipelines or when adapting to specific use cases. When we are talking about the flexibility of GPUs, actually it is the less flexible than the FPGAs, but more so than the TPUs. Actually, GPUs are the designed for the general purpose parallel processing, making them versatile for a wide range of AI workload, particularly those involving large-scale matrix operations like training deep learning models. When we are talking about the flexibility of the TPUs, actually it is at least flexible for the three. TPUs are highly optimized for the tensor processing and are the specifically designed for AI workloads, particularly deep learning models, while they excel in performance for the task. They lack the border programming, but GPUs and the FPGAs offers. Now, when we are talking about the performances, then we first consider the FPGAs. While FPGAs can be optimized for the specific AI task, their performance often does not match GPUs and the TPUs in terms of raw throughput. However, for the certain low latency, actually, to our power efficient task, the FPGAs can outperform GPUs and the TPUs, particular in case of the embedded or specific systems. Now, when we are talking about the performance of the GPUs are good middle ground in the term of the performance of AI. They offer parallel processing capability, which makes them great for the task like training large AI models and the running interference on the large data bases. They provide significant performance boost over the general purpose CPUs. When we are talking about the performance of TPUs, actually these are the highly specified for the deep learning task and can outperform both FPGAs and the GPUs for these specific workloads, especially when it comes to a large scale matrix operation. They are designed to provide the extreme performance for the AI model training and the interference, particularly for the deep neural network. When we are talking about the use case consideration, so FPGAs are the best for the high special application where flexibility and the low latency are the crucial, such as the embedded system, edge devices are the custom AI solution. And GPIs are the ideal for the general purpose AI workloads, especially training large scale model and the performing interference in environmental requirement significantly parallel to the processing. When we are talking about the TPUs, so highly effective for the specific deep learning task performance in cloud environment designed for the AI model training. When we summarize all the things, so we can say that the FPGAs are the more flexible and customized. GPUs offer balanced trade-off between flexibility and performance, and the TPUs deliver unparalleled performance for the deep learning workloads, but with the less flexibility. These are.
Okay, so how does an AI processor manage memory access to optimize throughput in AI computations?
Yeah, can you repeat?
Yes, yes. How does an AI processor manage memory access to optimize throughput in AI computations?
Yeah. So, like I've already told you that these AI processor are have their own on chip memory utilization system, and they have own they have their own GPU, CPU, and on-chip memories that is shared with that is like the caches, and that is the shared memory with them. So one is the caching, that is the data is pre-fetched and stored in the local caches, to close the compute units and reduce the memory latency. And there's another is tile-based processing. The large data sets are divided to the smaller tiles. So suppose that I have a data set of what's it uh, 1,000 or 3,000 numbers, like 3,000, 4,000 different values or numbers in the form of the data for the data sets. So if what it do, it's these all these 3,000 or 1,000 large data set are divided into small tiles, like it's that 3,000 or 1,000 data set divided into 500 small tiles. Tiles then fit into the chip memory with the frequent memory access, so that these small tiles will be transferred to the chip for the processing and then complete the processing. This is how this works. And then is the high bandwidth memory system, that is high bandwidth memory, or you can GDDR memory, that ensures the large amount of data that can be transferred rapidly with essential large scale matrix multiplication and the TensorFlow operations. And then is uh, another is data flow architecture. So many AI accelerators, for example, the TPU, use a special arrays where data flows through the array of processing unit and pipeline with in a pipeline fashion. And this ensure the continuous computation and minimize the overall memory uses. And there is another one that I have already told you, that there is a parallel memory access, that this is kind of banked memory system where memory is partitioned into independent banks, small banks that can be accessed simultaneously in multiple compute units, so that it can prevents the conflict between and ensures the uh, high output. And then is the thread level parallelism. So multiple of threads are wrapped to access different part of memory concurrently and fully utilizing the available bandwidth. So these are the things, that is how the AI processor manage and optimize the overall AI computation. I hope I have give you the answer to your question.
Okay, so what are AI chips designed for edge computing and how do they differ from traditional AI processor? I'm repeating the question. What are the AI chips designed for edge computing and how do they differ from traditional AI processor? सुरेश सर आप म्यूट पे हैं.
Yeah. Actually, AI chip designed for edge computing are specialized processing optimizing for running artificial intelligence algorithm directly on device at edge of the network, rather than they relying on the centralized cloud servers. This type of chips are tailored for the performance tasks like image recognition, voice processing, and the sensor data analyzing in real time, often with the limited power and the resources here. For example, location of processing. When we are talking about the uh, location processing of the
सुरेश सर आप म्यूट पे हैं.
actually all AI chips designed for edge computing are specified process optimizing for running artificial intelligence algorithm directly on the device at the edge of the network, rather than the relying on the centralized cloud server. These chips are tailored uh, on performance tasks like image recognition, voice processing, and the sensor data analyzing in real time, often with the limited power and the sources. For example, location of the processing. When we are considering about the edge AI chip, it is designed to perform AI computation directly on device such as the smartphone, cameras, IoT devices at the edge of the network. This minimizes the need for the data to be sent to the cloud for processing, reducing latency and the bandwidth use. They are ideal for application where immediate local decision making is necessary, such as automation vehicles, smart cameras, and the wearable designs. When we are talking about the edge location of processing for the traditional AI performance, so actually typically used in the center like data centers, cloud infrastructure, computing facilities. These processors are often more powerful and can handle large scale computation and the models that may not be feasible to run at the edge due to the resource constraint. When we are talking about the efficiency, power efficiency of the edge AI chips, actually these processors are designed to be externally power efficient, accommodate battery powered or energy constrained devices. They are optimizing power consumption to the external device battery while still delivering sufficient computational power of the AI load. Example includes NVIDIA Jetson, Google, Coral, and the Apple's a series cloud with the dedicated AI components for the for example, neural engine. When we are talking about the power efficiency of traditional AI performance, the AI chips in the data centers such as GPUs or NVIDIA A100 and TPUs are the more power hungry but are designed for the handle large scale training are the efficient tasks where power constraints are the less of the concern. Now, when we are talking about the computational power, so first consider the edge AI chip for the computational power. While these chips are the optimized for the power efficient and the local interference, they are generally less powerful than the traditional AI processor. So they focus on the accelerating specific AI tool such as image classification, object detection, and the neutral language processing with the hardware components like neural processing unit, NPUs, tensor power processing, TPUs, are the custom AI acceleration tailored for the specific edge use. When we are talking about the computational power of the traditional AI processor, it contrasts traditional processing like high-end GPUs and the TPUs are designed for more intensive, large-scale and AI computation, such as training, deep learning model, or performance high throughout the interference on large data sets. They offer much high higher computational power, but this comes at the cost of greater energy consumption and typically require a more substantial infrastructure setup. Now come on the latency and the bandwidth consideration. For the edge AI chips, so these chips are optimized to reduce latency by processing data locally rather than relying on the network communication with the distant servers. This is actually crucial. So, crucial application that require a real time or real time response, such as the autonomous vehicle, industrial automation, and the healthcare division. Now, when we are talking about the traditional AI processors in cloud or data centers environment generally deal with the much higher latencies as they involve sending data to remove server for processing. However, they can handle large volumes of the data in parallel, making them suitable for the task where latency is less critical and the data can be processed in the batches. Now come on the form factor of the integration. When consider the AI, so these chips are designed to be compact with the low power consumption and the small form factor to fit into the device with the limited space. Edge devices may include embedded system, wearable, or the other IoT devices, integration of the AI feature such as the machine learning model on the chip allows with the greater flexibility in the wide variety of the applications, often with the customer hardware accelerators that are tailored to the edge devices. When we are talking about the traditional AI procedures for the form factor and the integration, actually traditional processors are typically large and the more powerful, often requiring dedicated system or servers for the purpose cooling and the energy supply. And they come on the security and the privacy. In case of edge AI chip, large devices can be process sensitive data locally, reducing the need to transmit personal or confidential information to the cloud. And in case of traditional security and privacy, it is the AI processors in data centers can be secure transmitting sensitive data to the cloud or remove server raise privacy concern, especially if the data has to novel travel over the insecure network. So, and we can also take few examples on the subject. For few examples of the edge AI chips are the NVIDIA Jetson, Google Coral, Apple A series and the M series, Qualcomm Snapdragon. So in brief, AI chips for the edge computing prioritize power efficiency, low latency, compact form factor, and the local processing to enable the real-time AI capabilities in a wide range of the decision. While in case of the traditional AI, like GPUs and the TPUs, excel in high performance, large scale computation in data, focusing on raw power for the task, like training, complex model, and the handling vast amount of the data. That's all.
Okay, so can you explain the importance of low precision computation in AI processors?
Yeah. So in low precision computation or in AI process, what it means is you are doing the computation in int 8, that is integer 18, and then FP16, that is the floating point 16. So these int 8 and F16, that is the integer 8 and floating point 16, plays a crucial role in improving the overall performance and energy and efficiency of the overall AI processor. Because and also in the AI workloads, because of the various advantages of using this, that is especially needed in the AI workloads or ML workloads. So one of the advantages is the a smaller bit width. So as you can see here, 8-bit integer, int 8. It's the what comes under the low precision format, that is the int 8 and fp16, that's the floating point 16. So int 8 represents that there is 8-bit of integers, and then fp16 represents the floating point 16, that is the 16-bit floating point numbers. So it uses the fewer bits compared with the fp32, that is the 32-bit floating point integers. So if we use the int 8 or floating point 16, with it's used very small space. It can, and using these units, if we use this floating point 16 and int 8, if we use these low precision formats, then we can we can compute multiple of we can boost up the hardware space and multiple outs in the same clock size, rather than if we use the in compared with the floating point 32. If we use the floating point 32, then we might need more clock cycles for processing these floating point 32 units. So in the same clock cycle, we can fit the more space in the hardware, and that can and in the same clock cycle, we can do the multiple computation in the floating points 16 or 8-bit computer. And then as you can see, there is a smaller bit data bit size, like a smaller size, that is 8-bit integer of floating point 60, rather than the 32-bit floating point. So it is the reduced form of data. So data, it allows the data transfers and allows the AI processor to move the data across the memory hierarchies in very less amount of time. While if you use the FP 32, that is 32-bit floating points, it takes more amount of data, because it's the 32-bit of data, 32-bit of data points that we're transferring. Where in int 18 we are transferring only 8-bit of integers, or floating point 16, that is only 16-bit of floating points. So it's a smaller data size. So it allows the processor to transfer the data more frequently. And it's also, as it's a small size, because of this small size, we can do the calculation in the it's take less amount of clock cycles in compared with the 32-bit floating point or 32-bit integers. And second is the smaller data bit size helps in the reduce of data transfer latency and allowing the fast process. Third is the efficient caching, like the smaller because it's a small size, it can fit we can fit those value on the chip, or in the cached memory or the shared memory, in very small size. So it's also allows the efficient caching. And then the energy efficiency also provide the better energy efficiency be compared to the floating point. So these are the advantage that gives you the low what's a low precision computation, like the that is need that is one of the that is one of the most needful things, one of the most crucial thing for the AI, the latency, the faster the faster transfer of the overall things, and the better performance, and also helps you in parallelism, the parallel computation as well. So it's pushing up the whole overall processing that is needed by the AI. So it's better to use the low precision computation in AI processor like int 8 or floating point 60, rather than the fp 32 or floating point 32 uh, 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 for the AI computation.
So, what are the implications of using AI accelerators for energy efficiency and heat dissipation in large-scale AI systems?
So, in large scale AI systems, suppose that as you already in your laptop PC, if you have the TensorFlow units or the processor or GPU that you have laptop, might have seen the heat sink or the the cooling system out there in the laptop. So, and I might have and when you see the AI accelerators that is already there in the market, one from the few of the common accelerator that I've already told you, and Suresh sir have also indicated about those things. That one is the Intel neural network, Intel computer stick 2, or the Halloy AI accelerator for the Raspberry Pi and NVIDIA just are similar to those. Few from the brain chip packet, something like those. So you have noticed that don't have the cooling, they don't have the cooling compartment in there. If you notice the Intel computer stick, it's small USB size. You can search it right now in the internet. Small stick USB size, like the USB pen drive. I do not have any kind of cooling or fancy side. It's just a metal body that is what you need to be cool. So in compared of the energy efficiency and heat dissipation, the AI accelerator use very small amount of energy compared with those CPUs and GPUs or TPUs that is all there in the laptop. And the accelerator didn't dissipate much amount of energy that can be managed by the small heat sinks, and do not need sophisticated the fan cooling or the water cooling thing, or the cryogenic system, or cryogenic structure for the efficient cooling of their. They are very they consume very less amount of power as well, and also they don't produce much of the heat, and they can easily be managed with the heat sinks, and that those heat can be dissipated, whatever the heat can be dissipated, and this heat sink can further transport these to these heat these thermal thermal energy, or to the environment, and keep the overall chip cool. So in terms of energy efficiency and the thermal management, these AI accelerator are the better choice rather than the GPU, because these GPU CPUs are not only designed for the AI, they are also designed for the different works that need to be done by your system, that is the running the OS and checking the ports and many different tasks that will be done by that particular chip. So not specifically designed for that, but here the whole chip is specifically designed for and optimized according to the AI workloads and use, and optimized for the energy to computation ratio, and like I already told you, and the heat, so it also dissipates the less amount of energy compared to those GPUs. So these AI accelerator didn't need that much of cooling and sophisticated overall cooling structure or design in the hardware. It's simple heat sinks or some very low very cost efficient cooling system are enough for these AI accelerators.
Okay, so my last question for this session. How do you see the future of AI processor and accelerator evolving, especially with the advent of quantum computing and neuromorphic computing?
Actually, the future of AI processors and accelerators is poised for the significant transformation as emerging technologies like quantum computing and the neuroformic computing continue to evolve. Actually, these new paradigms promise to greatly enhance for the capabilities of AI, but they will also bring unique challenges and the opportunities for the innovation. For example, quantum computing and the AI processor. Actually, quantum computing, which leverages the principle of the quantum mechanism, superposition, interlongment, has the potential revolutionize AI by solving problems that are currently incredible for the classic processor. Actually, these are having some challenges also. Quantum computing is still in a infancy with the current quantum process limited by the noise and the decoherence, making them the unsuitable for the widespread AI application at the moment. It may take years or even decades before quantum computing reaches a level where it can directly enhance AI workloads. But as a quantum technology matures, hybrid quantum classical system could emerge, combining strength of the classic AI processor in the quantum acceleration. Another parameter is the neuromorphic computing and the AI processor. Neuromorphic computing is inspired by the structure and functioning of the human brain. Neuroformic process aim to replace the brain's neural architecture and the process to achieve more efficient AI, especially in tasks requiring pattern recognition, learning, and the decision. But it has also very great challenge. In case it is a scalability challenge. Although neuroformic chips show great promise for certain types of AI, scaling these systems to handle general purpose AI tasks is still a work. Another challenge is the software and the programming models. Neuromorphic computing requires new type of algorithm and programming models as the architecture of these process is radically different from the traditional AI acceleration. And the third parameter is the coverage of AI, quantum, and the neuromorphic computing. In the long-term future, we could see convergence of the quantum computing, neuromorphic computing, and the traditional AI computing. Another parameter is the AI-driven design of the future process. Another exciting development of the could be AI-driven of the future process as AI models become more sophisticated. AI might play a key role in designing new types of processing, including quantum chip, neuromorphic system, and even hybrid AI processing. These would allow AI to optimize hardware architecture, improving efficiency and the performance in the way that were previously unthinkable. So ultimately, the future of AI processor will likely to be characterized by increasing specialization as different types of the processes are optimized for specific AI tasks, and the integration between the classical quantum and the neuromorphic computing will unlock new capabilities for solving the most challenging AI problems. That's all.
Okay, so Ashwini ji, do you want to add something?
No, I think that's that was all what I also want to say, and so it's I have the same point that Suresh already told.
Okay, okay. So this brings us to the end of this session. I hope this was helpful to you all. And if you have any question, kindly post it in the comment section. We'll get back to you in the next section. Thank you.
Thank you.